Hello everyone, this is Dr. Ali, and in this session we want to talk about knapsack problem, and we want to see how we can solve this knapsack problem using differential evolution optimization. First, let's see what is this knapsack problem, and then we try to solve it using this algorithm. All right, so imagine that we have a knapsack which has a capacity. For example, here it says weight equals 7 kilogram, right? It means that it has like this much space that you can put different items in. Okay, and what are the items that we have? So, for example, here we have 4 items, but it could be different items as you like. And for each item, we have two values. What is the weight of that item, and what is the value for that item? For example, here it says this camera, its weight is 2 kilogram and its value is $1,000, for example, right? And for each one of the items, we have these two numbers. Now the question is, if we want to act smart and pick those items that if I put them in this knapsack at the end, it gives me the highest possible value that I can carry in this knapsack. So if you have this option to choose, what are those items that you choose? Okay. For example, if it's up to me to choose between the laptop and this vase, of course I go first for laptop. Why? Because look at the weight of the laptop, 3 kilogram, weight of this vase, 4 kilogram. So that is lighter. The laptop is lighter than this vase. Okay. And secondly, the value for the laptop is $20,000 and for the vase is 4,000. So obviously this laptop is much better pick than this vase because not only its weight is lighter, the value is much higher. So of course I will pick this. So let's see how we can formulate this problem into math language basically. So what we have is we have a variable, I call it xi, which is a binary. It can be either 0 or 1. And it says if it is 0, means that we didn't pick this item xi. And if it is 1, it means that we picked that item. So if we have n item here, right, in the previous example, we have 4, right? 1, 2, 3, 4. So it means n is 4. So, and each one of those i's is 0 or 1. So at the end, I need to find a sequence of these 0 and 1s. To be more accurate, I need four of these xi that correspond to each one of the items. That shows that, okay, either we pick this item or not. We want to maximize xi vi. What is this value? It says that if we have a sequence, we want to find the sequence xi that maximize this value. What is this value? This is the total value that we picked and put it in the knapsack, right? Because xi, we said it is either 0 and 1. So if it is 1, and vi is the value corresponding to xi. So 1 times value of it is v of, or the value of that specific item. But that's not it. We also have a constraint, right? We have a subject to this constraint. What is this constraint? We know that this knapsack has some limitation. We cannot just pick everything. We have a W max, which says what is that maximum space that this knapsack has. In our example, the knapsack maximum is 7 kilogram, right? So this W max is 7. And what is this part? It says XIWI. WI is the weight that correspond to this XI. If the XI is 1, it means that we consider the V or the value corresponding to that item as well as the weight because we put it in the knapsack. So it means the weight of that item is added to the weight of the knapsack. So this is the constraint, and this is the goal that we have, or objective function. And now there are different ways that we can do it mathematically. This is like an optimization technique that if we have an objective function and we have a constraint, we can combine them and have only one objective function. This is a Lagrangian method that this objective function uh, minus alpha, this alpha is just one coefficient that we need to tune it, then max of 0 and normalized way of this constraint. Okay, so what does this mean? If you divide both of these side of this, less than equal, divide by W max. This right side is equal to 1, and this left side is this part here. Now, if I bring this -1 to the left, we will reach to this term here, and less than 0. So this is a standard form for this Lagrangian equations, that if we have an objective function and then we have a constraint which is less or equal than 0, then you can combine it like this: minus alpha, max between 0 and this term. So you might ask, why you put max here? Okay. So this coefficient is basically, we added as a penalty here. So what does that mean? If in one of this sequence that we pick, right? Let's say the xi, we pick sequence for xi 0, 1, 0, 1. This is just one random pick. So if we see that this left side is less than W max, it means that those items that we pick, when we put it in the knapsack, we still see that there is some space in the knapsack. So there is no violation of this constraint. So if there is no violation, this term becomes 0. Why? Because this actually means that this guy is less than, actually this is a correct statement. If still there is some space in the knapsack, it means this term is a correct statement. So this part is actually less than 1. So something less than 1, -1, this term equal something negative. And maximum between 0 and something negative is 0. So it means we ignore this term here, right? So in other words, there is no penalty because we could fit everything in the knapsack and we didn't overflow. But consider another scenario. Imagine we pick another sequence, 1, 1, 1, 1, 4, 1. We picked everything. So when we picked everything, so of course that the weight of those items that we selected is more than the space or capacity of that knapsack. So there should be some penalty. That's not good. That's not good for our problem. We need to penalize this formula or objective function that, hey, this is not accepted. This is not a good actual solution, and its value should be something less than what is the value that we picked here. Because if you pick everything, it means that its value is maximum. So if you only consider this term and ignore this part, if you pick everything and we put it in the knapsack, what does that mean? So of course we get the maximum value because we picked everything. But then what's happened to the max? What happened to the constraint? We add this constraint with a negative alpha to see, look, if you pick a sequence that is above this capacity of the knapsack, you need to penalize this sequence, that its value, you need to lower its value, because otherwise it's always picked all the items. So if there is a penalty, then this term is something more than 1. Its value is more than 1. So something more than 1, -1. So of course this value is its value is more than 1. So maximum between 0 and a number which is more than 1, more than 0, of course it would be this penalty. So then we change its intensity with this alpha, and we reduce it from the value that it has for this sequence. So if you pick everything, then this value reduced by this term, because this term, it means that we need to penalize this selection. And then let's stop here, and then in next session I'll continue for the explanation that why we need to change this max to the mean. So I hope that's informative for you guys, and stay tuned for the next sessions. Have a great day, everyone.